Hey guys, it's me. You notice I look a little bit different than Jacob. I'm Landon. I'm going to be teaching your 430 recitation today. Super excited to talk to you guys about graph algorithms. So graphs are super interesting. Um, you'll use them in later courses in your coursework as a CS major or a CS minor. And we're going to talk about three of the more basic algorithms for traversing graphs, namely BFS, DFS, and Dijkstra's. Um, so first, I'm going to do some announcement stuff, and then we'll get into it. So, all right. So first on the announcements list. So your graphs homework has been released. It was a 2-week homework, and it will be due on Monday, April 13th. So that's actually 6 days from now. So it's been out for a little while now. My goal is to get you everything you need to finish everything on your graphs homework. There's only 3 methods. It is BFS, DFS, and Dijkstra's. That's why I'm covering it today. And my goal is to give you everything that you need so you can successfully do this homework. Feel free to ask questions in the normal way as possible, or in the way they've been doing them in the past. So that means basically going on Piazza and putting in the title, the date of the recitation, putting in the recitation folder on Piazza, and then I will answer it as soon as possible. Note that because I'm using Microsoft Streams, the delay is a little bit longer than it was on Twitch, so it may take me a little bit longer to get to your question, but know that I certainly will get to it. Okay, cool. So, what else? What else is on my agenda? So, yeah, this is your last homework, by the way. Once you're done with homework 10, it's completely done. Homework 8 was due last night, and we will be looking to give you grades back for that probably, I'd say, around next Thursday or something like that. Yeah, there's nothing too sensitive about getting your grades back to you because none of the coding is going to be asked on your exam 3 tomorrow anyways. So there's no need to give it back to you in a rush. Other things, exam 3 is tomorrow, right? Big news. So stay posted on all the announcements that are being posted on Canvas. That's your best resource as to things that are going on. I wouldn't stress about it too much. We made the format of the exam so that it's easier to transition from an on-paper version to an online version. We changed it so that it's 60 minutes instead of 50 minutes, so you have more time to kind of transcribe your diagrams back into the way that they're going to be done in the online exam. Hopefully you took practice exam 3. That's another great resource to check that everything on your end is working perfectly fine. It is open note, open homework, open any resource that we've given you in the class. And we kind of wrote the exam in a way that we want it to be open note because that way it's kind of a level playing field for everybody. And that way it can be as fair as possible. Let me see if I have any other announcements. Oh, Piazza will be shut down at midnight tonight. So that's what we normally do. So if you have questions, be sure to ask them now before midnight. Because once we shut it off, we won't reopen it probably until grading is done. So that'll be, yeah, it's probably Saturday or Sunday or something like that. So a lot of your graphs questions will be difficult to answer. So definitely keep asking away on Piazza. We're going to have a bunch of people online tonight answering questions. And that's the goal for you guys. So I think that's the end of my announcements. Besides, worksheets will be posted like they usually are under files, recitations, and then worksheets. So going for that, we are actually going to go into graphs intro first. Okay, so let me switch over to the PowerPoint slides that I have over here. Cool. Okay. So yeah, so we're talking about graphs. There's actually a lot more terminology than there usually is for some of the other data structures that we've talked about in the course. Neha did these awesome slides, and so I want to make use of them. So I'm using them again right now. So I'm kind of going to go through these fairly quickly. We mentioned the announcement earlier. You guys should have kind of already gone over them. I'll still go over them, but I'm doing it pretty quickly. Okay, cool. So a vertex. Think of a vertex as a position or a node in the graph, right? So 0, 1, 2, 3, and 4, those would all be vertices. They're nodes in the same way that you kind of had BST nodes in your other previous homeworks. Not on the fact that they, have to have 0, 1, or 2 children, but know the fact that they store data and they have pointers to other nodes that are in the graph, right? How do you get from one node to another node, one vertex to another vertex? You're actually using something called an edge. Edge is a connection between two vertices, right? So like it's showing you over here, between 0 and 4 is between 0 and 4 is an edge. Between 1 and 4 is also an edge. Between 4 and 3 is also an edge. Cool. Um, Another thing is that each edge we usually denote by a format called U and V. For U and V, one sec, I'm making sure that they're asking to make sure that I'm live at this time. It shows that I'm live, but let me see. I mentioned to my TAs who are on board right now just to make sure. I am live, just refresh. Okay, cool. Nice. So each edge is denoted by a U and a V. A U is where the vertex or where the edge is starting from, or it's kind of the origin vertex, and V is generally known as the destination vertex, right? So if you're going from 0 to 4, then U would be 0 and 4 would be V. Keep on going through. Undirected edge is an edge where U goes to V and V goes to U, right? So that means in a sense that I can go from 1 to 4, and then I could take this road back, and I could go back from 4 to 1 again. So this over here is an undirected graph. This one is down here as well because I can go to G to F, back from up to F to G, and so on and so forth. Cool. The other one that I wanted to talk about would be a directed graph. Directed graph is a case where the edges are directed, right? Where necessarily that I can get from A to B, but I can't get from B to A, right? There's no edge where that has a U as its B and a V of A, right? So there's no road that I can take to get back of here. Think of this as a one-way street where I can only get from A to B, and then I'm kind of stuck. Yeah, a directed edge U leads to V, but V may or may not lead to U. Yep, exactly. Keep in mind that with a directed graph, I could have an edge from A to B, and then also have another edge from B to A. But just having one to B does not necessarily mean that I'm going to have another edge from B to A, right? Cool. It just means that there is, in fact, a direction, that it's not implicit or explicit that there's an edge going in both directions. Cool. So summing all that up, a graph is a set of these vertices or edges. It's denoted by V, comma E, a set of vertices and edges. And we have two types of graphs, undirected and directed. I'm going to go ahead and move on. Cool. More graph terminology. So types of graph. Yeah. So weighted graphs. So while we saw on the previous slide that those edges didn't necessarily have a weight associated with them, you actually can have weights that are associated with these graphs. So for that, what's actually going to happen is that these edges, for instance, from F to G over here has a weight of 12, right? And that's just kind of associating a cost with going from F to G, right? And that cost could be anything. It could be distance. It could be a physical cost, something like that, right? Think of it as, let's say you're going from airport to airport. Well, hopefully not right now, but the weights of these edges could be, the distance of a flight from Atlanta to, say, Chicago or something like that. That would have a cheaper cost than the cost of or the distance of a flight that was from Atlanta to San Francisco, something like that, right? So we can kind of think of weights as being time or distance. We noted that up there. Cool. Now let's talk about sparse graphs. A sparse graph is a graph with that are few edges relative to the number of vertices. E is much less than V, right? And we can look at that over here, right? Each edge only kind of has one edge, or each vertex only has one edge extending out of it, or one or two edges coming out of it. It's very sparse in that nature. It'll make more sense when I contrast it with dense over here, where the dense graph is kind of the opposite. A graph with a lot of edges compared to the number of vertices, is in the edges is more comparable to the number of vertices squared. Right, so that'd be something over here. We can see that 4 has 1, 2, 3, 4, 5, 6 vertices extending out of it. All these other ones are quite similar. This being the case is a very dense graph. Right? Think of it as a dense cluster. Hopefully that terminology is not too difficult. I'm going to keep on rolling. A connected graph means a graph in which every vertex can reach every other vertex, right? That means that if I start at this vertex, I can get to any of these other vertex. That also means that if I start here, I can get to any other vertex, right? That's kind of the definition of connected, in contrast with unconnected, which means that from any given vertex, I cannot reach all the other vertexes in the graph, right? If I were to start it here, I can get to here and here, but I can't get to this vertex over here. That breaks the sense that this graph is connected, which means it is unconnected. Keep in mind that this also can hold true with directed graphs, right? If I had a, let's say, a directed edge from here to here, well, yes, if I started at this node, then I could get to all of these nodes because I took the directed edge over here. But if there isn't a directed edge back, well, if I start at this vertex right here, I'm actually stuck. There's no way for me of getting back from this edge over here to here, right? So we can keep on kind of going with those notions of connected and unconnected when we go forward with also having directed edges in our graph. Cool. Moving right along, in degree. An in degree is the number of edges going into a vertex. And this is the edges that have the vertex as a destination, or the number of edges that have the vertex as their v, right? We ran into that terminology earlier. If we want to think about it with, let's just say, let's say 5 over here. 5 has one edge going into it and another edge going into it over here. So that means that 5, well, it's not shown over here on the right, but 5 would have an in degree of 2. If we want to do it with one that is shown over here, 1 has an in degree of 0. There are no edges that are extending in to 1, but there are 2 that are extending out. Complete graphs are dense, e.g. a K6 graph. Complete graph. I just want to make sure I'm clear in the terminology. Yes, a complete graph would be considered dense, for sure. Yep, thanks for that question. Oops, I didn't mean to do that. I'm going to go back one. Cool. Okay. Contrasting in degree is out degree. And out degree is the number of edges that are extending out from a certain vertex, right? Think of those as edges that have the current vertex as the U, as in the origin vertex. So in this case, 1 has 2 edges that are extending out of it. Note that they're both going to the same vertex too, but those are both counted in the out degree as well. So the out degree of 1 actually is 2. If we want to do it with another one, let's say the out degree of 3 is only 1 because it has one edge that's going out, that's extending out of it. Keep in mind that the V of that edge actually still is 3, but it's still counted as having an out degree of 1, right? Cool. Oops, didn't mean to do that again. Finally, a subgraph, a graph G prime equals V prime comma E prime is a subgraph of G equals V comma E. If V prime is a subset of V and E is a subset of E, or E prime is a subset of E. We won't dive too much into this in this course. You will see it a lot more in algo or in more probably in combinatorics as well, or some other advanced theory classes. With that in mind, not a whole lot talking about subgraphs. Anyways, I'm going to keep on moving on. Cool. All right. Let's see. A cycle is a path of vertices that returns to the initial vertex. So think about in a directed graph over here. If I started at A, I get to B, taking this edge. I can go to C, taking this edge. And then from C, I could actually go back to A over here, right? And so for this would be considered a cycle because I can go around in the cycle right here. I have a question, though, from online. It says that amortized analysis is a worst-case analysis of a sequence of operations. But if it's a worst-case analysis, why do I always report the average case? Like add in the back of an rail says O of 1 amortized and O of n if you need to resize. Is this something different? Oops, the question just got deleted. Okay, I'll worry about that in a second if it gets put there and again. But anyways, I'm going to keep moving on. Okay. A vertex in the path is reachable from itself. Running out the path, only repeat the vertex you start with. From A to B to C to A, from B to C to A to B, to C to A to B to C. In acyclic graph, this is important. An acyclic graph contains no cycles, right? So that would be a case where if I start at any edge or any vertex, there's no way that I can get back to that vertex. And that holds true for all potentially vertexes in that graph. Note that a tree is just a connected acyclic graph. We've actually touched on graphs before with our BST nodes and our AVL nodes, right? Because we could access them from the root, and from the root connects to every other node in the tree. But once I dive deep into the tree, there's no way I can get back up to the root, right? And from that way, you can think of it as a connected acyclic graph. So now let's talk about how we generally represent graphs in terms of storing them and how we can manipulate them. One of the easier ways is something called an adjacency matrix. And this is a number of vertex by number of vertex matrix that contains the edge weights where I and j vertices have an edge between them with that weight, right? So that's best represented over here, right? So for this graph over here, if I wanted to get from 1 to 2, well, from 1 over here to 2, right, that would be this cell over here. It has a weight of 15, right? And that makes perfect sense. If I go from 1 to 2, I can see right here, it has a weight of 15. So this is an easy way of representing, given two vertices, what is the cost to get to that edge. Also note that along the diagonal over here, from 0 to 0, from 1 to 1, from 2 to 2, we all have zeros. Well, that's because if I wanted to get to 2 from 2, obviously that takes a cost of 0. So that makes exact sense. Cool. An adjacency list maps each vertex to a list of the vertices it shares an edge with. It's actually not really a list. It's usually implemented with a map. And you'll actually see that in your graph homework. What that'll be is it'll map a given vertex, right? It would map a given vertex like, think of it as A, and it would map it to a list of edges that start with the origin vertex being A. So in that one, A would be mapped to a list with B and then another one with E, right? Because it has an edge both to A to B and then also to A to E. Finally, if I just wanted all the edges combined, an edge list is basically just a list of all the edges that are associated in that graph. Not super complicated there. Cool. Moving on. Adjacency matrix. I did that over here. Adjacency list. Yeah, I think I honestly did a better job explaining it earlier. So I think we're going to keep on moving on. Okay. So over here, this is the graph terminology. Yeah, and honestly, I'm going to cover this stuff next week when I talk about minimum spanning trees. So actually, I'm going to break out of doing this slideshow, and I'm going to go over and probably move right over to, let's see, move over to the whiteboard to go over some of the things that we're going to talk about with the other kinds of traversals that we're talking about. Cool. So I'm going to head over there. Nice. Okay. Nice. All right. So going on over here, actually, I'm just going to make sure that. First, I'm going to make sure I'm going to flip this back to, this is not what we're covering right now. Easier. I didn't write anything on this slide. First, I'm going to go to breadth first search, right? Cool. Before I do that, I'm just going to check on the stream to make sure that it's still covering this. Make sure that it's still going. Actually, I'm sure it'll get there in a second. All right, cool. So we're going to talk about three algorithms today. The first being breadth first search, right? So breadth first search. Actually, I'm going to move my iPad just so that I can see if questions get asked to me and I can answer them live on the show. Cool. So let's talk about breadth first search. So breadth first search is the first of the three traversal algorithms we're going to cover today. All of these kind of follow the similar pattern, and you'll see that in a second. For breadth first search, it traverses the graph from a starting vertex, and it uses a queue and a visited set. So given a starting vertex in a graph, it's going to start at that starting vertex, and it's going to expand outward, and eventually it's going to return to you a list of vertices in the visited order. And in unweighted graphs, it's actually it could also produce a least cost path from starting vertex to other vertices. Don't really worry about that right now. That'll probably make more sense when I talk about Dijkstra's, and we can kind of return back to this. But in general, what we're talking about is that given a starting vertex and all the other edges and vertexes associated with that graph, using that starting vertex, we're kind of going to expand along a frontier, branching out from the starting vertex and kind of going in rings away from that starting vertex. It'll make more sense in an example, but I wanted to show you on the board here first. So kind of the pseudocode for the algorithm over here. We're going to jumpstart the queue by adding the starting vertex. We're going to initialize a visited set and a list. This is the list that we're eventually going to return at the very, very end of the method. And this is the visited set that we're going to be using to check if we've already been to a vertex before or not. And we'll see why that's going to be helpful in a second. Oops, I got a question. Can you move the board closer to the camera? Yes, I can. Yeah, what sucks about this is that I won't be able to see how this is. Yeah, can we get the writing a little closer to the camera? That's fine. Hopefully this is good. If not, I'll be able to check this in like 30 seconds when it goes live. Let me see how it is right now. Okay, I'm gonna keep talking. Hopefully it's better. You guys will tell me if it isn't. Okay, so I'm gonna go back to starting the algorithm again. I'm gonna jumpstart the queue by adding the starting vertex. So the queue is going to contain vertices, right? Make sure the generics on right on that when you're doing your homework. Then I'm gonna initialize my visited set. We'll talk about what kind of data structure is going to back that, and then a list. You have a choice of using either a linked list or an array list. You'll be adding to the back in both scenarios, so it doesn't really matter which one you choose, whether it be a linked list or an array list. Linked list is probably better because you don't have the amortized resize, but we wouldn't take off for either, as long as you're adding to the back. Then we're going to have a big overarching loop that basically says while, oops, someone's typing, hopefully that's good, while not every vertex has been visited and the queue is not empty. What does that mean? What that means is that while I haven't been to every single vertex in the graph, I haven't visited every single vertex in the graph. Think of it as if I started the Atlanta airport, I would have visited every single airport in America if I took a flight from somewhere to that airport, right? So that would be that first condition. And then also, assuming the queue is not empty. If the queue is empty, there are no more vertices to be reached. And at that point, the search would also terminate, right? This would happen, this terminating condition would happen actually in the event of kind of a sparse graph where the first terminating condition would happen more in the case of a super dense graph, right? I'm going to check to make sure on the camera this is a little bit better. Hopefully so. It looks a little bit better to me. So, okay, we're gonna roll with it. Okay. Once you've passed and make sure that either the queue is not empty and not all vertices in the graph have been visited, you're going to dequeue a vertex from the queue and you're going to check if that vertex has been visited. Well, how are you going to check if that vertex has been visited? Well, you can just call contains on whether that vertex is in the visited set. So using this visited set, what do we think would be the most efficient way to check if we've been to check if something is in a set that we've already been to? It'd actually be a hash set, right? If I call contains on a hash set, that's actually O of 1 performance, right? Assuming I have a good hash and the keys are distributed, right? So doing that, I can actually do an O of 1 check to see if I've been to this vertex instead of some people oftentimes will try and loop through their entire array list or call contains on their array list that they're eventually going to return. Well, to do that, it actually has to iterate over every single index in the array list, which would be a cost of O of n, right? So a big difference. And that's why we have, it does incur more of a storage cost to have the visited set, right? Because the visited set could be as large as size V, where V is the number of vertices, but it allows us to gain a huge advantage in terms of performance because we only have to do an O of 1 check to see if we've been to that vertex or not. Cool. Okay, so dequeue a vertex from the queue, check if visited, check if visited. If it hasn't been visited, we are going to visit this vertex, right? And I put visit in quotation marks because sometimes in visiting more advanced algorithms, you do something more when you visit a node, right? You may want to perform some operation or take note of something or something like that. Right here in this version of BFS, all we're going to do, we're visiting a vertex by adding it to both the visited set and the list that we're going to return, right? We're adding it to the visited set because now we have been to this node, we have been to this airport, and then we're adding it to the list because, well, now I know the order it took to get to this node as well, right? And so I'm going to add it, I'm going to append it onto the back of the list, right? Because the list is always going to contain the order from start to finish of how I got to all the vertices in the graph. Cool. Now, once I've visited that vertex, I'm actually going to add each of this vertex's neighbors that have not been visited yet to the queue, right? So that would be, for instance, if I'm at the Atlanta airport and I've just visited for the first time, I would say, okay, for every single airport I can get to from the Atlanta airport, I'm going to add that to the queue, right? So I would add JFK, I would add O'Hare Airport in Chicago. I don't know that many other airport names, but I would add those other ones, right? But only upon the condition that I actually haven't been to those airports before, right? Okay, cool. So I left this. I told you the kind of the intro. I went over the pseudocode for the algorithm, but honestly, breadth first search will make the most sense when we actually do an example of it. And I'm going to move over there and pivot to the viz tool to show you guys that. So I'm going to move on over here to the viz tool, move my iPad so I can see questions. Alrighty. Alrighty. Oops, let me go to that one. Okay, cool. Oops, I'm actually, oh no. I'm gonna move my face down here, make it a little bit easier. All right, cool. All right, hopefully we're on the same page now. I've done the transition. So now let's go over here and we're going to perform BFS on this graph, right? Okay, and I'm going to do it with a starting vertex of A. Notice how I have to give it a starting vertex of some node in the graph. If I gave it a starting node of Z that doesn't exist in the graph, obviously that wouldn't make much sense. So that's exactly why we do it like that. Cool. All right, so now going back into it, I'm going to go and say, I'm going to run this on the graph, and I'm going to initially pause. Okay, cool. So breadth first search. First, what it's going to be doing is it's the current vertex is A. In the queue, I've actually added B, C, and D to the queue, right? And notice that the order I added those in was actually the order here. It actually depends on what the order is in the adjacency list, right? In the adjacency list, in the order was DCB, well, then that would be the order that it was in queue to the queue. Here, it looks like the order was B, C, and D, right? So I'm going to play, and I'm going to dequeue from the queue. I'm going to see, oops, and then I'm going to add D and then as well E, right? So notice how I had all my the queue contained all the vertices that I could get to from A, right? So that was B, C, D, and then E, and in that order, right? Generally, we like to follow the convention of the ordering that we follow is alphabetical order, right? So B would be before C, which would be before D, which would be before E, right? And that would be what would map to A in kind of an adjacency list. Cool. So I have all of these vertices, and now I'm going to dequeue from the queue. Notice that it dequeued the first thing in the graph, and so that would be a B, right? So it dequeued a B, so that'd be the first thing. Oops, I got a question. How can you tell if every vertex has not been visited for the while loop in the BFS algo? Great question. We will know that we visited every single vertex in the graph. Well, I could do something super silly and check every single vertex in the visited list against all those vertices that are in kind of the data structure that's holding all the vertices. Or I could do something much smarter and know that, well, I could just compare the size of the visited set to the size of the number of vertices in the graph as a whole, right? And doing that comparison, grabbing the sizes of one, grabbing the size of both a hash set and a list is going to be O of 1, and comparing those two, I can tell an O of 1 if I've already visited every single vertex in the graph, right? So great question there. Really appreciate that. Cool. All right. So notice how I've dequeued B. B was the first thing in the queue, and so now I'm going to see that in my list I've actually added B because I started A and I went to B next, right? So now I can see from B, what I'm going to do is I'm going to try and attempt to add all of B's neighbors. Note that I've already actually been to A. A is already in my visited set. So I'm not going to add this edge right here going from B to A. In fact, I'm actually going to go from B to G, and that's going to be the only edge that's added to the queue, right? So that one's not going to get added, right? But this one over here is. That's because G is now in the visited set, but it wasn't right before. Right, so now, super cool, I'm going to dequeue again. Notice how I dequeued from the queue again. I went up here to current vertex. Now current vertex is C. I added C to the list over here. I appended it to the back of the list, and now I can see that I'm going to attempt to iterate over all of C's neighbors. C only has one neighbor. It's an edge for get from C to A. Well, note that I've already been to A before. A is already my visited set, so because of that, I'm not going to add this edge going from C to A, right? So really, C doesn't get to add any of its neighbors because all of its neighbors, all of its one neighbor, actually already exists in the visited set. Right? So cool. I'm gonna step forward here. Okay, A has already been visited, skipping, nice. And then now I'm done. I'm gonna dequeue D since that was at the head of the queue. I dequeue D, I add it to the back of my list, right? So now the order that I've been to nodes is A, then B, then C, then D. I'm going to attempt to add all of D's neighbors back into the queue. So I'm going to attempt to add A. That's not going to work, right? A has already been visited, skipping. Now I'm going to add F because F has not already been visited, right? So what's going to happen now is it's going to add F both to the queue and then to the visited set based on the algorithm I described before. Boom, right? So now I've visited F. I visited F because I've enqueued a neighbor that has its destination being F. And I've enqueued it to the queue so that I can dequeue it in due time and hopefully visit it. Cool. So now you can see that if right now I'm done iterating over D's neighbors. So now what I'm going to do is I'm actually about to dequeue from the queue again. What I'm going to be dequeuing next is going to be E right here, right? So I'm going to step forward. I'm going to dequeue E. Nice. Add that to my list. So now I've visited E. I'm going to attempt to iterate over my neighbors, A and G, right? I've actually already been to both A and to G, so I'm actually not going to end up adding anything at all. So I'm step forward. Yep, A's already been visited. G has already been visited. Cool. So now I'm going to dequeue G from the queue right here. Add G to my list. So now the order has been A to B, A to C, then A to D, A to E, A to G, right? And then now I'm going to do is I'm going to iterate over these neighbors. Notice I've already been to B, that's going to fail. I've already visited F, so that's going to fail. The only one that hasn't been visited yet is H. So the only thing that'll be added to the queue after this will be H over here. Right, so cool. It's going to fail with B. It's going to fail with E. Oops, I forgot about E. It's going to fail with F. The only thing that's going to work is with H. Right, so now I've visited all these nodes in here. I visited all these nodes. And actually, I correct this, I talked about this earlier. Don't terminate the algorithm until you've compared the size of the array list to the size of the number of vertices in the graph. Because if you're enqueuing, if you're adding edges to the visited or vertices to the visited set when you're iterating over neighbors, then right now, see for instance, it thinks I've visited every single node in the entire graph. Well, they're in the visited set, but I actually haven't added them in my list over here. I still have yet to add F and H, right? So I want to compare the size of the list to the size of the number of vertices in the graph, not the size of the visited set, right? Just use that as better convention. If you're adding the visited set when you dequeue, that's another implementation. Then you could compare visited set and array list alike. And here, because I'm iterating over the neighbors and adding the visited set then, I actually need to be comparing the size of the list to the number of vertices and not using the visited set. Cool. So now I've added G. I've appended to the back of my list. I've enqueued H as a neighbor, and now I'm going to step forward. I'm going to dequeue F. Cool. F is my current vertex, appended on my list. I'm going to try and iterate over its vertices. I've already visited them, so no surprise here. It's going to fail. D has already been visited, skipping. G has already been visited, skipping. Cool. So now what I'm going to do is I've iterated all over F's neighbors. Now I just dequeue from the queue again. That'll be now, it will be H. I dequeued H. Yeah, the current vertex is now H. I've appended H to the end of the list. I'm going to attempt to add G. That's going to fail, right? And then now notice I've visited every single thing in the list. And so now the algorithm is going to terminate. Right, cool. Queue is empty, done. So in this case, the queue being empty took priority over visiting all vertices in the graph. That's just because of the order of the terminating conditions. It wouldn't really matter in this case because the queue emptied at the same exact time I visited every single vertex in the graph, right? So that's super cool. Okay, nice. Yeah, let's go back to now. We're going to go back to the whiteboard, and I'm going to talk about the efficiency of the algorithm. Right, cool. I'll be there in a second. Alrighty, let's get back to it. So I'm going to flip my iPad around. Nice, over here. Okay, cool. So we're talking about breadth first search. Kind of the last thing that we have to touch on is the complexity of breadth first search. Right? What is the cost of doing breadth first search? And oops, no question. How should the BFS algorithm handle an unconnected graph? Well, in the case of an unconnected graph, actually this would be the terminating condition that would fail. The queue would be empty, right? Because think about it, if I had a graph that looked something like right? If I were to start at this, or let's just say this node right here, this is A, then I would NQ, these, I'd eventually visit this one, I'd visit this one. Well, the queue would be empty, but this terminating condition would never, I would never be in a circumstance where I visited all the vertices in the graph because I can't get to these other two nodes over here from A. So what actually would happen is the queue would run dry before this terminating condition up above, right? So, but in the case of a kind of a sparse graph, like you mentioned, the terminating condition that would come into effect would be the queue being emptied, not every vertex being visited. So, good question there. Thanks for asking it. Okay, now let's go back to the algorithm. Yeah, I was talking about efficiency. So one thing we're talking about efficiency of graph algorithms, it's a little bit different than how we've talked about it in the past with other algorithms. We kind of have to represent it in the case of both talking about vertices and talking about edges, instead of in the case of, let's say, AVLs or something like that, just talking about it in terms of the nodes, right? Because we want to be able to compare both a sparse and a dense graph, right? And if we only use one of those, we only talk about the number of vertices, but we're not really talking about the number of edges, which is fairly important when we're discussing algorithms for on graphs that could in fact be dense and have a lot of edges that are spanning from each vertex. Cool. So with breadth first search, really what we're talking about is we're not going to be done until, in the worst case, of adding all the started vertexes or adding all the vertices in the graph to the eventual list that we're going to return, right? So we know right there that we have a cost of v, right? So this is O of v, and I'm doing these little lines over here. This just denotes the cardinality of v. The cardinality is basically a fancy word for saying the number of vertices in a graph. We also have to consider the number of edges, right? If we really had a really dense graph, like I just showed earlier on the PowerPoint slides, and for every single vertex, it extended out to every single other vertex in the graph, well, we'd end up adding a lot of edges to the queue. In that case, well, how many edges could we add at most? Well, we'd have to consider at most E edges, as in all the edges, right? Because when I go to a node, I'm at least considering all of the edges that are neighboring away, or that are spanning from that vertex, right? So if I'm going to visit every single vertex, I will have at least considered all the edges in the graph, right? That doesn't necessarily mean I'm adding every single one of those edges to the queue, but I've at least considered them. I've iterated over them when I'm iterating over my neighbors. Cool. So this is actually going to add a cost of E over here as well, right? And you're asking, well, Landon, what about the worst, best, and average case? Well, good thing to know in terms of efficiencies and complexities. With graphs, really, there's only one complexity, right? So the only thing you'd have to know, oops, I dropped my marker. The only thing you'd have to know if we were to ask you a complexity of graphs on an exam would be to know that it's, for BFS at least, it's the cardinality of V plus the cardinality of E, right? Something in that regard. Cool. Let me think about some extra notes on breadth first search that I had right over here. Yeah. Oops, I got a question. So if the queue empty condition will terminate the BFS algorithm, why do we need to compare the size of the list in the graph? So what the question earlier is what happens if the graph is sparse? Well, in the case of the graph being sparse, not the queue will empty before I visit every single vertex. So that's how I want to terminate the algorithm. I can't dequeue another vertex from the queue if another vertex doesn't exist, right? I would use the other condition is if I've already been to every single vertex in the graph, in the case of a connected graph, well, I don't want to keep on iterating over the other edges that may be kind of left to decay in the queue if I've already been to those vertexes in the first place, right? If I've already visited a vertex and I dequeue it from my queue and I've already visited it, well, then what was the point of that at all? So if I know that I've already been to every single vertex in the graph, there's no point to consider any of the vertexes that are left in the queue. So in that case, I terminate the algorithm. So I don't have to, in the case of a very dense graph, I may have a ton of vertices left in the queue from, instance, let me switch up this graph a little bit. Right? If I were to start over here, then now this is B, I started at B, then from B, I would go up here to, let's say, A and C. So A would NQ D, or actually, will be a scenario where that would happen. Yeah, this would still work. So I would go to A, I would NQ D, and then before then I would go to C, and then I would NQ D again, right? So in that point, there would actually be, well, depending on how you, if you're doing the visited check, it actually would make a difference. But in the case of a dense graph, you're going to have more vertices in the queue after you visited every single vertex in the graph, if it's still connected and dense. So because of that, we terminate the algorithm, and we kind of handled the sparse case by having the queue being empty, and we handled the dense case of seeing the size of the visited or of the array list that we're eventually going to return versus the number of vertices in the graph. Hopefully that was a good explanation. I kind of stumbled a little bit, but anyways, we're going to go from there. Okay, other notes about breadth first search. A good thing to note about breadth first search is that it kind of explores nodes in frontier, right? If I were to start at B and go on from there, well, then at first, I'm only going to visit nodes over here. I'm going to visit all these nodes that are 1. I'll add some other nodes over here. E, F, something like that, right? Another thing with breadth first search is that when I start at B, kind of think about it as a frontier, is that I'm only ever going to access all the nodes that are 1 edge away from the start before I access any vertex that's more than 1 edge away from the start. So A is 1 edge away, C is 1 edge away, D is 1 edge away. I'm never going to get to E or F before I get to, because they're 2 edges away, before I get to every single vertex that is 1 edge away from that starting vertex. So because of that, I kind of use the term frontier, is that this is the initial frontier of all of the vertices that are only 1 edge away. And next, later on, I'd expand that frontier to kind of include E and F. And now those are going to be all of the edges, and actually this node over here, right, because this one's only 2 as well. But by doing that, you're going to explore all the nodes that are a certain number of edges away before going to any node that is more than that many edges away, right? So I'm going to explore every single vertex that is 1 edge away before I touch any vertex that's 2 edges away. I'm going to touch all vertices that are 2 edges away before I reach anything that's 3 edges away, so on and so forth like that. And because of that, it's actually what we're doing here is kind of like a level order traversal in our BSTs or our AVLs, right? What it's doing is in that scenario, right? Think about it like this, something like that, right? Initially, I started this node over here, and then my next frontier is right here, right? These are all the nodes that are 1 edge away, right? 1 edge away from that initial node. Then after that, I'm going to touch all of the nodes that are more than the next frontier, right? All of these are 2 edges away. So in that regard, we're actually doing a level order traversal. Level order traversal is really a breadth first search on a tree, right? So that's cool to note. Any other super cool notes? We use hash sets because they're on 1 axis. I already talked about that earlier. If you want to know a fun fact, a popular benchmark on a lot of supercomputers is running BFS on a really, really, really large graph. I didn't know that until I became a TA for the course, but if that interests you, cool, go for it. All right, I'm going to keep on going on because I have a lot more to cover. Wow. Depth first search. Depth first search, also a way of traversing a graph from a starting vertex. Uses the same visited set and some sort of stack. Some implementations use a physical stack, but in this case, we use the recursive stack instead. This intro is the exact same. I'm using a visited set. The only thing that changes here is that I'm using a stack instead of a queue to negotiate and traverse the graph, right? Other implementations will use a physical stack. We're requiring you to do this recursively. Use the recursive stack as a means for traversing the graph. The algo is very, very much similar. Basically, if the current vertex has not been visited, you visit that node, you add it to both the visited set and the list, and then for each of the current node's neighbors that hasn't been visited, we're actually going to, instead of adding it to the queue like we were doing before in this algorithm on this line, what we're going to do here is recurse on this neighbor. Keep in mind, if you ever want to pause the video and go back to it, you can totally feel free to do that. I know there's a lot of text on the whiteboard, but I want to show you, I want to just save time by writing earlier instead of later. So we're actually going to recurse on this neighbor. And because of that, this is kind of does the opposite thing that breadth first search does. It's going to do a deep dive down a path of vertices instead of kind of being more hesitant like breadth first searches and kind of expanding in frontiers. I'm actually just going to go straight into the viz tool because I think that's the most helpful thing. But if you have questions, feel free to ask them. All right, let's go over here to the vis tool. Okay, so I'm going to run it on A again. What's happening now? What is the VS in breadth first search? VS is visited set, right? And I'm going to use that same convention probably when I talk about a lot of other algorithms as well. I just don't want to write out visited set every single time. But if you ever see VS in BFS, DFS, or Dijkstra's, they're all representing the visited set. Cool. All right. So I'm going to run this on A. The first thing that A is going to do is it's going to mark it as visited, add it to the list, and then it's going to recurse. It's going to attempt to recurse on its first neighbor, which is B. Right? So let's see that right now. I'm going to pause it. Its first neighbor is B. It's added A to the visited set in the list. It's going to recurse on B. Right? This was the recursing on the neighbor that I mentioned earlier in the pseudocode. When that happens now, is it's going to go to B. It's going to do the same thing again. Notice how we're about to dive down this string right here, this path right here. I'm going to go to B. I've added B both to the visited set and the list. And now what I'm going to do is I'm going to iterate over my neighbors again. Notice the first time I'm actually going to iterate over my neighbors. The first neighbor actually is A, but I've already been to A. So I'm not going, there's no need to recurse on it, right? So it would fail that visited set check right there. Cool. So we'll see that right there. Vertex A already visited, skipping. What it's going to do instead is going to recurse on G, because G is its first neighbor that it hasn't visited before. So it's going to do that right then. It's going to go to G. It's going to add G both to the list and the visited set. Cool. And then from there, G's going to do the same thing. It's going to go try and go back to B. It's already been to B, so that's going to fail, right? So we can see that right there. This is part of G iterating over its neighbors. So G's going to go back to B. That's going to fail. B's already been visited. Cool. Now it's going to go to E. E has not been visited yet. So it's going to recurse in this neighbor. It's going to keep on diving down this path right here. Cool. Going to step forward. Nice. Now we're to E. Current vertex is E. I've appended both E to the list and the visited set. And now we can kind of see that what we've done from here is we've really just dove down into this path right here. Instead of in PFS, we would kind of be expanding more in a frontier manner like I described earlier. Here, you just kind of send it. Once you get to a node, you just tunnel down that path until you hit something that has already been visited, in which case you kind of pivot and go backwards. So we'll see that right now with E. Because E, both its neighbor A, right? A has already been visited, it's going to skip that. And G has already been visited, it's going to skip that. So now E is done iterating over all of its neighbors. It's actually going to, this recursive call is actually going to terminate, and it's going to go back up to G, who's still waiting to recurse over some of its neighbors. Right, so we'll see that right now. G has nothing else to do. And now we're back to this recursive call on G, right? G is now about to iterate over its other neighbors, right? It iterated over B and F, and it dove into a recursive call with F, but now it has to go to F. I may have said F earlier when I meant E, but now it's about to recurse on F over here, its next neighbor that has not been visited. Cool. It's about to recurse to F. Yep, that makes sense. F hasn't been visited, so it's going to dive down there. It's going to add F to the visited set and the list. I haven't visited all the vertices, and I sure as heck haven't finished all my recursive calls. So now I'm going to iterate over F's neighbors. Its first neighbor is D. Have I been to D? No, I haven't been to D, right? I'm about to recurse to D because I haven't visited it yet. Now I'm going in that recursive call right here. And you can kind of see this string of recursive calls down here, which is very, very helpful when navigating through the recursion here. Now once I'm at D, I'm going to add this to the visited set and to the list, right? That's super cool. Now I'm about to iterate over D's neighbors. D's already been to A, D's already been to F. So this recursive call is going to terminate in a second. Skipping, skipping, skip. Now I'm going back to F. F's going to attempt to iterate over its last neighbor, G. It's already been to G, so that's going to fail, right? And now I'm actually going to go back to the recursive call on G that I did before, right? Because G still hasn't iterated over its neighbor over here, H. It's still waiting to do that, right? So now I'm going back to G, I'm iterating over its neighbors. So go to H. H has not been visited. I'm going to dive down the rabbit hole. I'm going to visit H. I'm putting it to both the list and add to the visited set. Cool. I'm going to try to attempt to iterate over H's neighbors. It's only G. I've already been to G. Nothing too interesting is going to happen here. This is just going to terminate. Cool. I'm going to go back to G. G's actually done iterating over its neighbors now. So this recursive call right here is going to terminate. Cool. Now I go back to B. Well, B iterated over its neighbor A a while ago, and it iterated over G, as we can tell. So actually, B's recursive call is also done now as well. Cool. I understand that DFS is like constructing a path and visiting every node through a deep dive. Wouldn't DFS break for a case of an unconnected graph? How should we handle such a case on our homework? Well, in the case of an unconnected graph, what will actually happen is that you'll just be left with an array list that doesn't have all of the vertices in it when you eventually return it. And that's perfectly fine. That's what we would expect in a graph that's disconnected, right? If I had this vertex X over here, DFS would still operate on from starting at A, and it would still visit, I would still want to get all of the vertices that I could visit from A in the order that I visited them. But if I can't get to X, that's fine. X just will not be in the list that I end up returning, right? So think about that. Cool. Now I'm back to B. B's done iterating over its neighbors, and I finally get back to A, which started like an hour ago, and it iterated over B and went down this huge rabbit hole, right? It went over this huge rabbit hole, but it still has to iterate over its neighbor C over here, right? So what that's going to happen now is going to go to C. It's going to realize C hasn't been visited yet. It's going to add that both to the list and to the visited set. And now C is going to attempt to iterate over its neighbors, right? If it's already been to A, so that's going to fail, right? It's going to skip there. C's already, now it's iterated over all over its neighbors. That call is terminated. And now I'm going to go over from A, and I realize that now D has already been visited, so that's going to fail. And then E has already been visited as well. And then now I have my list of what I visited in what order using depth first search. So I went from A to B to G to E, panned back to G, went to F to D, went all the way back, backtracked, G went to H, backtracked all the way up here, and then A went to C. Right, that's what's kind of happening over there. Cool. So unless we have any other questions, I want to make sure I get to Dijkstra's. It's the most complicated of the three, and I want to make sure we have the most time to it. I'm going to go over complexities first, but that shouldn't take too long. Okay, back to the whiteboard. Alrighty. So now let's talk about the complexity of depth first search. And really, it's the cool thing about depth first search in terms of its complexity is that actually, let me make sure. Yep, it's the same thing. In terms of complexity, it's actually the exact same as it was for breadth first search. In essence, I want to visit every single vertex. In a perfect world, my end list would have all the vertices of all the vertexes in the graph. That's going to be initially a cost of V. So I have the cardinality here again. But we also have to notice over here that I'm also, from each vertex, I'm trying to iterate all of its neighbors again, right? When I'm doing that big for loop. And when I'm doing that, in essence, that is also going to incur a cost of E as well. I have the hiccups now. So now we have the cost of E, V plus E, which is the same as our cost of breadth first search. And that really makes sense. I'm doing basically the same thing. I want all the vertices in my list, and I'm iterating over all those neighbors. And by doing so, I'm incurring a cost of not only just all the vertices in the graph, but also the cost of all the edges as well. I have a other question. DFS. How do you know which neighbor to traverse down first? Awesome question. That's really, really important. We know which vertex to dive down into first based on the order that is given to us in the adjacency list, right? So you may be thinking, well, if the order of these things the order of things in the adjacency list was different, would it change the result of our DFS? Yes, 100% it would, right? If I had a graph that was going from, let's say A to B to C over here to D, if A in the adjacency list was mapped to B, then C, then D, well, then I would go to B, then go to C, and then go to D. If in another universe it was like this, D, C, B, well, it would actually be the opposite order. I would go to D, then to C, then to B. So the order of the adjacency list matters, and I denoted that, yeah, I noted down here. The order of the list is dependent on one, the kind of stack you used, I'll mention that in a second, but two, the order of vertices in the adjacency list. And that holds for BFS as well. Because of that, because we're diving down that rabbit hole, it really is dependent on what order we do get neighbors from our adjacency list. So that's an awesome question. And note that in your homework, you have an adjacency list. That's a data structure that you're given. So you don't have to worry about really what order the neighbors are doing in it. We've already done that work for you, right? All you have to do is iterate over those neighbors and add it to the list. Right, so we've done a little bit of the heavy lifting there for you and constructing the graph in a way that it's easily navigable. I've already talked about efficiency. I talked about the notes. Note that another thing is that if I'm using a physical stack instead of a recursive stack, well, in this case, I would add, if I was at A, I would add B, then C, then D. If I was doing a recursive stack, I would dive all the way B and then on all of its that path like that. If I was using an actual stack, then the stack would look something like B, then C, then D, and then I would actually pop D first on my stack. So the order would be D. This is my array list I'm eventually going to return. D, and then I would pop C, and then I would pop B, right? As opposed to if I just use the recursive stack, it actually is going to do in the opposite order, right? So depending on whether you use a recursive stack or a physical stack, the order returned by your traversal is going to be different. But in this homework, we're requiring you to do it recursively. We require you to do it recursively, and if you do it iteratively, you're going to lose probably nearly all the points for DFS, unfortunately. So be sure to make sure you do this recursively, not iteratively. I'm going to stop talking about DFS, besides making a side tangent of in order, pre-order, and post-order traversals were basically another version of DFS. In the same regard that level order traversals were kind of a version of BFS on trees as well. Any other fun facts in my notes? Nope, I think I got everything. Dijkstra's. Cool. Let's talk about Dijkstra's. Dijkstra's is one of the more complicated algorithms we're talking about in the course. And what it does is it really strives to answer the problem, okay, well, I can tell the easiest path to get to somewhere if my edges have no weights, but what about in a world where all these edges do have weights? And I want to consider the cheapest cost to getting from one start vertex to all the other vertices in the rest of the entire graph, right? Pretty cool stuff. So actually what's going to happen here is it uses actually a lot of the same mechanics as BFS does. And Jacob loves to talk about this, and he says that basically the algorithms we teach in this course are just a bunch of version modifications on BFS. And that basically is true for Dijkstra's. Dijkstra's is a version of BFS just intended to work on directed graphs that are weighted, right? There is one stipulation though. It will only work with non-negative edge weights, right? So given a start vertex and a graph with only non-negative edge weights, find the shortest, lowest cost path to every other vertex in the graph. When I say non-negative, well, you may be thinking, okay, well, why didn't you just say positive numbers, Landon? Well, I could just say positive numbers, but also edge weights of 0, weight of 0 is valid, right? So that's why I said non-negative. -1 is not fine. 0, and we'll see later, actually is completely fine and valid. Cool. Okay, so this also works on unweighted graphs. Think of all edges having a cost of 1, right? So think of an edges where there are no weights. Well, you can think of them having no weight, or every edge has the same weight. So you could do this on another graph on an unweighted graph to do the same thing. But in that case, you might as well just use BFS anyway, so there's not really a huge point. This utilizes 2 data structures, right? More than we had before. Well, utilizes PQ version and a hash map and the visited set. And so actually 3 data structures. We're tacking on one more than we were using before. It uses a priority queue of vertex distances, I'll mention that in a second, and a hash map and a visited set. The visited set, you're already familiar with. We used that before in BFS and DFS. The hash map is actually for mapping, I talked about it before, is that it's mapping vertices to their cheapest cost from start vertex, right? So that would be if I started at A, then every single key in the map would be all the other vertices in the graph, and those vertices would be mapped to the cost of the cheapest cost to get to them in the graphs, right? So B might be mapped to 1. If I could never even get to the vertex X, it'd be mapped to a cost of positive infinity, or map an integer to underscore max value, something like that. But I'm mapping K to max to, or A maps to C means the cheapest cost to get to the vertex A from the start is 6, right? Showing you that mapping there. The other thing is a priority queue of vertex distances, right? Before we're using a queue in BFS, well, we kind of need to maintain some sort of priority to these edges, to these weights. So by doing that, we're going to use a priority queue, basically a min heap and a trench coat of vertex distances. You may be saying, what the heck is a vertex distance? A vertex distance is basically a special data structure we've given you to make it easy for you to do Dijkstra's, and you'll see why in a little bit. right? If I mention vertex distances later on, I'm basically going to abbreviate it with VD just because I don't want to write out vertex distances every single time. But think of a vertex distance as basically only having a vertex and a cost, right? So it has a vertex and a cost. Cool, right? And basically we do that. We don't really care about, and this is the destination vertex, by the way, because basically all the vertex distances we're thinking of, they all are kind of stemming from that original starting vertex. So we only really care about the ending vertex, and that's the most important thing. So we have that. It's in your homework. I'll probably get to describe it later if I have time. Who knows if that'll happen. But I'm going to keep on going down to the algorithm because I think that's important. So initially, what you're going to do is you need to initialize the cost to get to every single vertex in the graph to starting out to be positive infinity, as in you can't get to every single vertex in the graph, right? So that means in your code is actually going to be initializing, mapping every single vertex to having a value of integer.max value to begin with, right? Because you can't get to, you're basically saying, okay, the starting vertex is on an island and I can't get to any other nodes because I don't know if I can get to any other nodes. So by default, the cost to get to each one of them is positive infinity. Okay, so that's the first step. And now you're going to kind of jumpstart the priority queue in the same way you were jumpstarting the queue in BFS by adding a vertex distance. This is actually going to be a VD to PQ with weight 0, right? So that's basically adding an edge or a vertex distance with a starting vertex, let's say it was A, with a cost of 0, right? That's just basically saying I can get to A and a cost of 0, which is completely true, right? If I'm at the start vertex, to get to the start vertex is the cost of 0. So that makes complete sense. Cool. So I actually have the same terminating conditions I had before. While the priority queue is not empty and all vertices have not been visited. Having both of these terminating checks is actually very, very important, right? Because one handles the case of a sparse graph, not empty, like I talked about at BFS, and the other one handles the case of not all of them. This handles the case of a sparse graph, and all the vertices have not been visited. That's handled in the case of a dense graph, where I don't want to be iterating over more vertex distances than necessary when I don't have to. When I've visited already a vertex in the graph, I've already found what the cheapest distance to get to every node or every vertex in the graph already is. So there's no reason to continue considering vertex distances at that point. Okay, I'm going to dequeue a vertex distance, same thing I was doing in BFS, and I'm going to check that that vertex associated with it has not been visited. That's just doing a check on the vertex distance vertex versus the visited set that I initialized earlier. Okay, so then I would mark, assuming that it hasn't been visited, I'm going to mark that vertex as visited, and then from there, and then keep in mind that all of this is in the same if statement. I should have indented it over a little bit. Yeah, this should be indented a little bit to the right. But basically, if a vertex distance has already been visited, you don't want to do anything. The same in BFS, you're just going to continue and just dequeue another vertex distance, right? So assuming I haven't visited this vertex already, I'm going to mark it as visited. And then what I'm going to do is I'm going to iterate over each of my neighbors that hasn't been visited, right? So that's the same thing using the adjacency list on that given vertex, right? I'm basically going to say, if the new total cost to get to the neighbor, the distance from the current distance to the current vertex plus the distance from the current to the neighbor. You're saying, what the heck does that mean? Well, that's saying that if I had a, I'll move this right here. A was my start, and to get to B took a cost of 3, and to get to C over here took a cost of 5. Well, the vertex distance to get to B would be a vertex distance with vertex B cost 3, whereas to get to C, it's actually not only just the cost to get from B to C, but it's actually the cost, I have to sum the cost of getting to A to B and then the cost of getting to B to C, right? So the vertex distance associated with C would actually be a vertex distance of 8, right? Because I'm summing both the 3 and the 5 to get a total cost of 8 to get to the vertex C, right? So if the new total cost, right, that's one I just calculated, let's say it was 8, is cheaper than the mapping in the hash map, as in before, C was probably already mapped to a initial cost of positive infinity. If this new cost is cheaper, as in is 8 less than infinity, then I want to override that mapping in the hash map. So I would say I would call my hash map hmap.put C, comma, and then the new cost of this new vertex distance, right? After I've done that, after I've updated the cost in the hash map, I'm actually going to add the new vertex distance with a new total cost, that total cost of 8, to the priority queue, right? And by doing this over and over and over again, I'm doing basically a very similar thing to BFS, but now I'm incorporating weights as well. I want to very quickly get to going over the algorithm in visualization tool. So I'm gonna move over there and pivot over there really fast. That's really, really important for you guys to see. Cool. So back to the Viz tool over here. Alrighty. So now we see we're back over here in the Viz tool. I have my graph already set up. Notice if you go on the Viz tool right now and you go to Dijkstra's, it actually has this graph already pulled up. So if you want to pull up these graphs alongside me, should have probably said that earlier, but I didn't. You can totally do that and start, do all the same steps alongside me. So I start vertex as A, cool. So I'm gonna start at A. First thing I'm gonna do is I'm gonna initialize all of the cost to get to all the other vertices to be infinity. Notice that I didn't click pause quick enough and it already put in a cost to get to B is 8. But for all the other vertices, I can see that initially what I did is I just mapped all the vertices to initial cost of integer to max value, or infinity in this case. And what I did is I jump started the queue with a, actually, I'm going to restart this for a second. I really want to see, I'm going to drop down the animation speed really, really low. Oops, I'm going to hit run. I'm going to hit, yeah, so I've initialized all the other vertices to be infinity. A is mapped to 0. So that means I've jump started the queue. So the priority queue has this value of A, 0. Cool. So I'm going to do now is I'm going to step forward. I'm going to dequeue from the priority queue. That's the first step. By doing so, I'm going to get to and be able to update the cost of A in the distance map right here. Cool. And I'm going to iterate over A's neighbors. I'm going to add A to the visited set over here. We'll see that. A is been added to the visited set. And then now I'm going to do is I'm going to iterate over these neighbors right over here, right? And so in this case, what's actually going on is I'm going to go in the same order I'm returning the adjacency list. That would be, first I'm going to add a cost to get to B of 8, right? We'll see that right now. Now this new distance of 0 plus 8, 8 is less than the old distance of infinity, so I'm going to update that in the graph. Cool. That's going to be updated 8. I'm going to add 8 to the priority queue. Nice. Now I'm going to do the same thing for C. The cost of 0 plus 2, the cost to get to A is 0, plus the cost to get to C is 2. 0 plus 2 is 2. That cost is going to be cheaper than infinity, so I'm going to update this in the priority queue as well. Cool. Then from there, I'm going to add that to the priority queue. Nice. Same thing with D. See how 2 moved up in the priority queue because it's cheaper than 5. D is going to be a cost of 5. It's going to update in the distance map. And then cool. Now I have all 3 of these things in the priority queue. I'm going to dequeue from the priority queue. I'm going to dequeue the cheapest vertex distance in the priority queue. Right now, that's C with a vertex distance of 2. So what's going to happen there, I'm going to dequeue this. This is orientating the priority queue, so it's ready for next time. It's going to dequeue this C over here. It's going to check, have I already visited C? No, I haven't visited C because it's not in the visited set. Cool. So I'm going to add it to the visited set, and now I get to iterate over its neighbors. So first I'm going to go back to A. I'm going to realize, okay, well, I've already actually been to A. There's no reason to even consider any vertex distance to get there. Because of how I'm doing this, if I've already visited a node before, there is no way I can possibly get a cheaper path because I'm taking the cheapest vertex distance at every single point anyways. So if I would have gotten a cheaper cost to get to A, well, I would have already found it already. So there's no reason to consider A at all here. Cool. So I'm going to go to B now, and so now I'm going to add a vertex distance of 2 plus 1. There's a vertex distance of 3. I'm going to actually update my distance of B in the distance map because 2 plus 1 was cheaper than the old distance of 8. Going from A to B was a cost of 8, whereas going from A to C and then C to B, 2 plus 1 is 3. That's cheaper than the original weight or the original cost to get there, or of 8 that I just showed. So I'm going to add that to the priority queue. Cool. B, that's going to go to the front. And then I'm going to add it, E as well. I'm going to start to go a little bit faster here. That's going to be updated with 5, and then added queue with 5 as well. Cool. Now I'm going to dequeue from the priority queue again. Nice. Current vertex is B. I haven't visited B, so I get to care about its neighbors. Cool. I'm going to iterate over A and C. I've already been there, so I don't care. Boom, boom. D, I haven't been to yet. So now I have a new cost of 2 plus 1. The original cost, the cost right now to get to B is 3. Plus 1 is 4, is actually cheaper than the old cost of 5. So I get to update it in the hash map. Cool. Then from there, what I'm going to do is I'm actually going to add one more of G. I'm going to add a cost of 10, G with the cost of 10 to the, that's going to go to the top of the priority queue. I'm going to add cost of 10 to, oops, someone's saying I have an issue to the stream. And I have a question in Piazza as well. How do we store the positive infinity in the distance map? Just use integer.max_value. The same thing we were kind of using, we've kind of fiddled around with in other assignments. We represent infinity in this course with the largest possible value for ints. That is integer.max_value. Cool. OBS is dropping frames. Mine says it's dropped 0 frames. So that's interesting. Anyways, I'm going to keep on going because I'm running low on time. Okay, cool. Going back here, I'm going to add G with a cost of 10 to my priority queue. After I update it in the map, this gets added. Cool. I'm going to DQ again. D with a cost of 5 is the cheapest option. Now I'm going to go back. I'm going to iterate to A. I'm going to iterate to B. They've already been visited. I don't care. And then from there, because yours is working. I can help Jacob in a second. Okay, going back. Sorry about the delay. Making sure this stream for 6 is going to be working fine. Okay, so now it's going back here. I don't care about B or A, so I'm going to step forward. T is out of the visited set. Don't care about A, don't care about B. F I do care about. And now I have a cost of 2 plus 1 plus 1. So my current cost to get to D is 4. So I've looked up that cost in the map. And now I'm going to compare that, add on the new cost. So I'm looking, what's the current cost to get to D is 4. Tacking on the new cost to get to F, right? That's the cost of that edge. So 4 plus 4 is 8. Is that less than the mapping to get to F in the hash map? If it is, I don't care. Or if it is, I'm actually going to update it. All right, so I'm going to update this to be 8. Cool. I'm going to add that to the priority queue of 8. Another question in registration questions. Cool. Then from there, I'm going to DQ. Now I'm going to DQ this edge of 5. Notice I've already been to 5. So what happens now when I DQ 5 is that I've actually already visited it, right? So I'm going to disregard it. I'm just going to DQ another thing from the priority queue. Cool. So I go from there, I DQ E. From E, what's happening now is that I have a cost of, I haven't been to E before. Jacob's having problems. Then from there, I'm going to go to current vertex is E, right? I haven't been to E, so I'm going to iterate over its neighbors. I've been to C, so that's fine. I don't care. I'm going to add a cost of the current cost of E plus 2. 5 plus 2 is less than the current mapping to get to G, so I'm going to update it in the hash map, and I'm going to add that to the priority queue. Cool. Now from there, that's it. I'm going to DQ this from the priority queue because it's the cheapest thing now. I'm going to visit G officially. I'm going to iterate over its neighbors. I've been to B. I don't care. I've been to E. Also don't care. Been to F. Notice I have an edge weight of 0. Nothing's going to break here. What I'm going to do is I'm going to add a cost to, currently the cost to get to G is 7. Plus 0 is still 7. So 7 is actually cheaper than 8. So I'm going to update that in the hash map. And I'm going to add to the priority queue. Cool. From there, I'm going to go to H. H currently has mapping infinity, so obviously this is going to, 8 is less than infinity, so that's fine. I'm done entering over neighbors, so I'm going to DQF. And DQF, cool. Now I've gotten the cheapest possible way to get to F. I haven't visited it yet, so now I'm about to add it to the visited set. Yep, and then I'm going to iterate over its neighbors. I've already been D, so I don't care. I've already been G, I don't care. H, over here, actually already has a cost to get to it as 8. Well, I can also get to it, I already have the current mapping is 8. Well, if I can get to it and also in a cost of 8, that's not better. So I'm actually discard that and not even going to add it to the priority queue. And then from there, I'm going to go back to DQ again, get to B. I've already visited B, so I'm going to disregard this, right? I've already been to F, so I'm going to disregard this again. I'm going to get to H. I haven't been to H yet. That's fine. I'm going to add it to the priority queue. And I'm going to attempt to add its neighbors of F and G. Well, I've already been to F and G, right? So I'm not going to add them in the priority queue. And now we notice that I've actually been to every single node in the visited, or I've been to every single vertex. Every single vertex is in the visited set. Because of that, I'm going to terminate the algorithm. I'm not going to consider G of 10 in here. Because by visiting every single node, I've actually confirmed that I've gotten to the node in the cheapest possible cost. Sorry for going a little bit over. I'm going to quickly talk about the efficiency of the algorithm, and then I'm going to hand it over to Jacob in a second. Cool. Efficiency. Efficiency of this, I don't have a ton of time, so I'm just going to write it down. Efficiency of this is O of V plus O of E log V. All right, let me just make sure that I did that correctly. O of E plus E log V. Cool. Yep. And this is because it's basically the same cost as BFS, but this log V is for the priority queue and the cost of always having to NQ and DQ to the, all right, this is the cost of, NQing and DQing to the priority queue, right? I'm going to talk about very, very briefly about how non-negative edge weights do not work. So starting at A, what would happen is initially I would take the cheapest path to get to C over here, which is -1, and then I would get to D with a cost of -8. Or actually, sorry, I would not do that. I would go to B first with a cost of -2 because -2 is cheaper than -1, and then from B, now the cheapest cost would be -6, so I would take that and get to D, right? Well, in fact, if I had actually gone to C with a cost of -1 and then added this to get a cost of -9, a cost of -9 is actually better than a cost of -6, right? And actually, if I were to go around again and again and again, the cost to get to these nodes would actually become increasingly negative, right? It'd actually be a negative feedback loop or a negative cycle. And whenever you have a negative cycle, basically the cost to get to D would be negative infinity. So you cannot have negative edge weights when you're talking about dextrose. It's very, very important. See, were there any other notes that I mentioned? Intuitively, dextrose is a general relation to BFS for weighted graphs. The edge weights can be thought of how many edges are there between vertices, and the priority queue acts as a queue, takes into account this information. I think that's about it. It's a greedy algorithm. It's taking the cheapest vertex distance at every single instance. And that is about it. I'm going to go back to the computer and talk about a little bit of homework notes before I help Jacob. All right, I know I'm going a little bit over. I'm sorry about that. But I want to make sure that I give a chance to talk to you about these homework notes so that you have the best chance of tackling your homework. So in terms of your helper classes, edge, this is just a class representing your edges that, it has a U and a V and a weight. A vertex has data. Vertex distance has a class representing the distance to a vertex from a current vertex. Probably the most useful thing, especially for dextrose, its useful methods are get vertex and get distance, the two things that are associated with any given vertex distance. A graph represents a directed graph with a vertex set, edge set, and adjacency list. The adjacency list is how we represent the graph. So to get all the neighbors from a certain vertex to all the vertex that it's neighboring, you basically would call get on that vertex in the graph. It would give you the value. The value would be a list of all the vertexes you can get to from that given vertex. Cool. Maps each vertex in the graph to a list of neighboring vertices and vertices it shares an edge with. It's limited with a key of the vertex and a value of the list of vertex distances, right? Given a vertex, you can use this structure to obtain a list of neighboring vertices. Deliverables. For graph algorithms, you need to implement BFS, DFS, and dextrose. BFS to return a list. You create a queue to keep track of vertices. You can do graph.getAdjacency list.getCur to get neighboring vertices, right? That's what I'm talking about. The adjacency list is given right here, and then calling get on it with the current vertex will give you all the neighboring vertices, the vertex distances of vertex cur. DFS is very, very similar. Do not import java.util.stack. And then dextrose over here returns a distance map that holds the shortest distance found from a given start vertex to every other vertex in the graph. Initialize map with the values of 0 for start vertex, integer max value for other vertices. Vertex distance is very useful here because you can get the distance to a neighboring vertex You will have to create a priority queue to traverse the graph and a set to keep track of vertices you visited already. That's kind of information you knew above in BFS and DFS, except for the priority queue and the map. We already talked about that earlier. All right, I know that was a whole lot. Hopefully that was helpful. If you have more questions, I'll stick around for a couple more seconds. I'll wait around for a minute or so for you guys to ask questions. If not, I'm going to leave this over here on this graph homework explanation. I know it's a little bit rushed at the end. BFS, DFS, Dijkstra's, and graph terminology is a lot to ask for in one recitation. Sorry for going a little bit over, but we'll be there next week to help you with the other graph algorithms, mainly spanning tree algorithms. And for tomorrow, feel free to ask questions up until midnight tonight. And good luck on your exam, guys. You guys are going to kill it. So I'll wait around for a couple more minutes. Probably won't ramble just because no one wants to hear my voice anymore. I'm actually going to drink of water. My throat is dry. Alrighty. I haven't seen any other questions yet, so I think I'm actually going to kill the stream. If you want to look at Jacob's 2,